transit and 30% the remainder will be using car. This is the mode choice that we have here. So whenever you do the mode choice model, one of the challenges would be to compute. So in the survey, when you ask question, they give you information on the chosen. Okay, so if I took car, I can tell what is the travel time per car. But my competing usually is not available. Information for that is not available. So that's something we have to alternative. You only have one alternative information, the other three alternatives have to be compared. So that sometimes can take time, or sometimes we need to do that clearly. So in this case, we use Google Maps on the paper. We add some API running based on the departure time of the person. So they provided that they can by the bus or to row. We found travel time for that corresponding time for the hour. So that's what we did, and we had to generate a service based on the origin postal code and the university designation. So this is the initial mode. So here we are choosing between car and okay. So car is the base, so we only have utility for the so the different age and age where so you will see and two variables to account for non-linearity in detail. Okay, so age has a linear effect negative transit, but there's also a positive squared part that can reduce the little bit the function. Then we also the individual if the faculty member or the staff member or the student. So students are most likely to transit, staff are next, faculty are least among these three categories. The full-time members of communities are likely to use transit. In Quebec, the license system is a little different. What it means is usually in any province or state in Western Canada, usually you get better license. You pay $10 or $15 for a couple for 5 years or so. But in Quebec, they include insurance as part of the driver license. So it's expensive to get a driver license. Basically, if you don't want to drive, people don't get it. They can get a state ID, which is will serve as an identification purpose. But if you get a license, usually it's because you're driving. So that's what you see here. If state is active, you are less likely to use transit. So you will see a strong impact there. You may initial waiting time. All of these are as expected. You would expect travel time, transfers, walk time to have a negative impact, and that's what we notice here. Even initial waiting time. So here we were able to capture different components. So initial waiting time, walk time, transfers, and so on. So all of these have an impact on the model. Okay. And we here log any questions? Yeah. So if you use only age as a linear function, you only goes up. That's great thing. But you want to capture any curves, right? You want to turn it around. So as age increases, the utility for transit drops. But the point you should take for that to be possible, you need to do a so for continuous function, you use polynomial forms to see the relationship non-linear across. So if you so this would be the relationship for age. But now with age and age square, may represent something like this. The point where it will start going down, but this will happen after also, so we don't really have to worry. But it is representing that relationship you can capture using agent. Yes. So, no, for a parabola, the sign of linear no, if it is positive, if the h square is also negative, the parabola will go up, right? It won't come down. It has to be positive. They have to be different signs, right? This is the relationship. It will go like this. For it to come down, for it to taper, you need to have no, no, that's the both. First is 45 weeks old. In the utility equation, you will do 45 minus 0.4. Similarly, 45 square times 0.002. Both. So that will give you the yes. No, wow. Even so, walking time is fixed time. Whatever is walking time, that much what is figured. Yeah, there are only two alternatives here. Car and transit. So if this is negative, what it means is that they are going to use the other car. Yes. Here it is the travel time for. So this is an interesting data set because the uh, only the transit people for the 1200 or so transit people we actually looked at ruptures. The reason we did this is because there is commuter rail, metro, and bus. There are many ways you can go from A to B. So some of them can use a completely bus route. They can use completely commuter rail and walk. Commuter rail, metro, and bus. So there are many combinations that you can use. So for some people, there are 7 to 8 combinations of transit alternatives that they can take to arrive there. Okay. So we're trying to model that. So what we see here is uh, because the route itself is not well defined, right? So when you are looking at car versus transit, one alternative is car, the other alternative is transit. That is clear. But here, all of them are transit routes. So there is no label. So that is route 1, route 2, route 3, route 4. So the name, they are not labeled alternatives. Okay? So the name itself does not have. I cannot estimate constant because in a car versus transit choice, I can estimate constant for car or transit. But here, because these are simply routes, each route itself does not mean anything. It's just a combination of different transit alternative bus. Does this have metro? Does this train? So if a route has transit that has bus, that parameter will kick in. Otherwise, it won't kick in. Okay. So you will see that among the 3 alternatives, metro is the preferred alternative. Okay. So people prefer alternatives that have metro in them. So versus bus and train. Train is the least preferred. So if you use train, if it is train as part of the route, usually that is the least preferred. Okay. And again, here we are looking because we are looking at different transit alternatives. We wanted to see travel time between these transit alternatives is definitely perceived. So we looked at the coefficient for travel time bus, metro, and train separately. So you will see that travel time in bus has the highest negative PPD. So people don't like spending too much time in the bus. Metro is the most preferred. Train is okay. Okay. We also looked at walking time squared. Again, same idea. We looked at walking time squared. We also looked at number of transfers. As you would expect, number of transfers has a significantly negative impact. So people don't like routes where there are more transfers. Then there is waiting time for transfer, and we also looked at some interactions. Female interacted with travel time is positive, saying that women are less sensitive to travel time than men. Same thing with age. Faculty are negative, so it means faculty are more sensitive to travel time than others. Okay, so those are some infections. Okay, so we tried for
this one, what is the rationale behind choosing the variable?
So when you have any continuous variable, it is good practice to track. So I am showing what turn out to be significant. Like if a square is not turn out to be significant, I drop it. Yes. We write and whatever comes significant, we do. We also did some elasticity analysis here to see how changes to transit time and car time influences the probabilities of them. So we are looking at scenarios where transit will benefit. So you'll see time initial waiting time. You can see the impact on overall changes to the mood. That's what we are showing. And you'll notice the highest impact is for household vehicle ownership. You reduce household vehicle ownership by 1, that will have a substantial impact on and any questions? So far model where we are one model for analytics. Okay, but in 7 we they need to explore more information. So what I mean by that is if you spend one model, one coefficient of travel time and one coefficient of travel. So what we see is that sensitivity to travel time is same for everybody. The beta is the same for everybody. Same thing for travel cost also. We are posing the condition that everybody, but it might be younger individuals might be different, or different from low income individuals, or people who live in areas might be different. So look at age as an important variable. For example, let's say I'll do a model separately for everybody under 45 and everybody over 45. Model separately for low to medium income and it's easy to do, or you can do something about gender, so you can do males and females. So if you do that, you will get separate log likelihoods for both of them. You can add them and compare to the single model. So because in a single model, you are saying that the coefficients are same for everybody. But when you do a separate model for men and women, you are saying the beta coefficient for travel time for men is different than women. So you are increasing, you actually double the number of coefficients, right? You are making limits. You are estimating, let's say, 6 coefficients. Separate models, unrestricted model. We are saying coefficient is different for women. So we are giving extra. So you can compare the L1 plus L2 that you will get will be the log likelihood for the unrestricted model. That you can compare with the restricted model by doing the likelihood ratio. Okay, that will show which is the, if you need separate models. Yes. Yeah. So the sample size will be however you split it. So if there are 70%, 60% in men and 40% women, for example, 60, but log like, when I am comparing log likelihood, when I right? So when I compare it to the combined model, I'm doing an apples to apples comparison. And then efficiency change. So there is some interest that we need to get some of the differences for high income and low income. And so coefficient men and women, it's tricky to say. Travel time, I think women are less sensitive, so you will see that coefficient will be smaller, less negative for women. Same thing with cost also, they might be less sensitive. There might be some differences. Now, if you do it with low income and high income, value of time is higher for high income, so you will see the beta 1 and beta 2 update in a way that beta 1 or beta 2 value of times will be higher for the 2. So that maybe impact of transfer will be more for high income. So you'll see the coefficients change, then you can check with your intuitive expectation. Now, should it change? For some of them, it might not change. No, if L is higher, then you don't need, because we don't L1 plus L2 be higher because closer to 0, right? So negative, there is negative magnitude. So L1 plus L2 will always be higher than L2. Okay, but it should be sufficiently higher because you have more parameters in L1 plus L2. In L you have, let's say, K parameters. In L1 plus L2 you have 2 K parameters. So it has to be better by a significant amount for it to be used. That's what we can test the probability. Yes, the actual test. So when you take the difference, 2 times, yeah, difference of 2 obliques. When you get that value, you look at how many extra parameters you have in the unrestricted model. You have 6 and 12. Difference is 6. So you look at the chi-square table for 6 and 80% of difference. That should be more than. Now, this approach is very straightforward in the sense that, I mean, if you know how to do one model, you can do 2 models. It's not complicated. But, so I'm showing, but you could actually do this in a single system. Okay. So what you can do is you can interaction with male and female and in your models. So you can actually do all of this in a single model by capturing those interactions appropriately. So this will allow us to see which is actually so you have travel time, beta time, then you add another beta times travel times gender. You can have B for drive, let's say, beta naught, given travel time. Okay, so now what we'll do is we'll add a new coefficient, TTN, which is TT times male. So this is there for everybody. This is there only for men. Okay, so if we do this, if beta TTM is negative, it tells you men are more sensitive. If it's positive, they're less sensitive. So if you do this, you don't need to do it in separate model. You can do it in a single model. And if this is insignificant, then you are not different. If it is significant, you know they are different. So this will help Instead of only doing 6 plus 6, you can actually test whether the 6 will be significant or not. So maybe you'll end up with 6 plus 2. So only 2 variables are different for men and women. So you'll have 8 variables in your. So this is an approach. But yeah. Yes. You can say both of them are the same. Yeah, you cannot do anything because, like you said, they're different. So that's why you have to do the logic. Because whenever you compare two things, they should be using the same number of observations across. Okay, because otherwise it won't be bad. So if you're only doing one or two variables, you're saying only the number of women low income versus high income, you can consider segmentation one. You can consider segmentation. So this works okay, but if you have somebody might say, okay, why only gender? Why only income? So you can start adding more variables. So you can add gender, income, location, vehicle ownership. Okay, so this is let's say 2 categories, 3 categories, 3 categories, and 3 categories. So now the number of samples you have to make starting with very quickly. Right? So for this it will be 54, 2 times, 3 times, 3 times. So you have to do 54 separate models. Okay, that is not very efficient because first of all, some of those samples will be so small. You have only 1,000 data points. If you break them into 50 samples, you'll have a lot of data, lot of samples with 5 records, 10 records, and so. Okay, so it's not very efficient. So exogenous segmentation, the way we are segmenting it, once well, you're doing it, maybe 3 up to 4 or 5 samples. Okay, but if you want to consider a variety of variables, the segmentation approach does not work very well. Okay, so to address that, there is another approach called endogenous segmentation or latent class models or latent segmentation. Okay, so in that the idea is we don't segment based on independent variables. We actually segment with a focus on the dependent variable explanation. Okay, so here when I segment it the way I'm doing, I don't care if I'm doing the better job on more choice. I'm saying men and women are different. I'm saying low income and high income are different. But it's not necessary that is correct. We don't know. We're not testing that in any form. But in an endogenous segmentation way, what we do is we separate people into segments if it helps us explain our mode choice better. Okay, so our focus is how can I better predict or better understand my independent variable. With that in mind, can I come up with a smart way of segmenting the population? Okay, so we usually in that approach we go to 2 or 3 segments, but the segment membership is a function of different independent variables. It's not just one variable. Here we have everybody can tell who goes into which segment because men, women, so or high income, low income. So a single variable determines segment membership in this process. But in an endogenous model, you are actually using an equation determine segment. So let me show that. It's easier to the example. So let me keep talking the case study and then I'll come back to the math as well. Okay, so this is a model on endogenous segmentation. So here we are looking at mode choice of intercity travel mode choice. Okay, so we are looking at how do people travel from Toronto to Montreal corridor, and we have information on social demographics and trip-making characteristics. We also know level of service data that is available from. So this is the how the data looks like. So there are 3 modes: car, train, vehicles per day on average. Air, there are 25 flights going between that location. And we have the cost. You will see cost per train is cheaper, air is expensive, and car is between them. Then you have in-vehicle time. So obviously in-vehicle time for air is the smallest. Train and car are comparable. And then out of vehicle time for air is the highest, right? Because as you know, security and whatnot, or getting to the airport, all of that has time associated with it. Car has the smallest out of vehicle time because you have access to it immediately. Train also has. Okay, so again, it's a traditional mode choice model. You are just looking at these aspects. But what we are trying to do here is we are not trying to segment the population based on income or any one variable. We are trying to see, okay, are there segments in the population that are function of different independent variables? Okay, let me show you the segment and I'll explain. So, the segments itself take the form of multinodal logic. So, we are here saying that there are three segments. Okay, so segment 1, segment 2, and segment 3. Segment 3 is the base, and we are estimating the effect of different variables on segment 1 and 2. So if you look at, for example, female, okay, which segment are female riders most likely to like based on the numbers you see? The base is 0. Okay, this is negative. Right? So that has the most likely the females will be in segment. You are traveling alone, which segment are you likely to be in? If you look at traveling alone,
First segment.
so it's not the first segment, it's the third segment, because third segment is 0. 0 is higher than both negative values, right? So you have to think of it that way. So if you are traveling alone, you are likely to be in the third segment. Weekend travel. If you are traveling for a weekend, where are you going? Segment 2. Okay? Then income. If you are high income, you are going to segment 2. Okay? So what you will notice is each segment has its own characteristics. So if you look at segment 2, it's women not traveling alone. So people going as a group, we can travel. Okay? So segment 3 on the other hand is people who are going alone, who are less sensitive to cost because of their high income, they are not in. Okay, so that's what it would be. Backlinks is low, I think.
Yes.
Everybody behaves the same. But here, when you are creating the segment, we are saying you have 3 personalities and 3 choices. You can behave 3 ways. But the same person. So I'm putting the same person in 3 ways. So in each personality, the choices are different. So maybe if I'm in segment 3, I will fly because time is very important for me and I'm going for work. If I'm in segment 2, I'm going for holiday. Time is not that important. I can take the car or the bus. If I'm in segment 1, I'm neutral to everything. I might do everything equal. Okay? So these are the shares of each segment. You can see, you can estimate that there are 49% of the people go to segment 1, 49% of the time, 12%. So very small percent goes to segment 2, 39% goes to segment 3. So if I look at the weights and average that out, this is what you get from the weights. Okay? So now let me show you how people in each segment behave in terms of mode choice. So before that, let me give you more characteristics. So we talked about this. So look at the characteristics of the independent variables in each segment. For people, when you are in segment 1, look at the income. The highest income people are in segment 3. Right? So high income more likely to be in segment 3. Look at the female variable. Overall market is 0.2, right? This is 0.2. Look at the proportion of women in segment 2 is 0.4. So predominantly women go to segment 2. Similarly, traveling alone is 0.7, but segment 3 is 0.77. So more people in the personality are going there. Same thing for weekend travel, everybody is in segment 2. Trip distance, again, segment 3 has the longer trips. People who make longer trips are in segment 3. Now these are more choices. So given they have 3 personalities, how do they behave in each personality? Look at segment 1. Okay. Segment 1, segment 2, segment 3. The constants are also a little different. Let's talk about constants later. Let's look at in-vehicle travel time and motor vehicle travel. If you look at segment 2, travel time is not even significant because they don't care. Okay? But if you look at segment 3, it's significant and substantially higher than others. So this is 0.02 here, 0.06. So they're more sensitive to travel time in segment 3 and less sensitive to travel cost. Okay, so travel cost is here. You'll see this is sensitive to travel cost, more sensitive to travel cost, least sensitive to travel. So we are saying 3 different behaviors. If you come to segment 1, you care about money and travel time. If you go to segment 2, you don't care about travel time, you care about money. If you go to segment 3, you don't care about money, you care about travel time more. Okay, so these are employed folks traveling for work. These are women and holiday people traveling during weekends. These are others, basically. There are somewhere in the middle group, that normal group traveling for that. Okay, so if you estimate a single model, we cannot capture all of these variations. By doing an endogenous segmentation, we are able to capture variations in behavior across different variables. So here your frequency also impacts are different. So here frequency has much larger impact than the other two. Now if you look at the constants, segment 2, look at the constant for air. Segment 3, it's significantly positive compared to segment 1 and segment 2. Same thing for train also, it is positive. In segment 2, they are not flying. They are likely to use train. Car is the mix. Car is 0. You have 3 alternatives, you can only consider 2. So basically, if it's positive, it's more than car. If it's negative, it's less than. Is that okay? Any questions? So this is an approach where we created 3 segments, and the segment membership is not based on one independent variable. It's actually several independent variables. We looked at gender, we looked at income, we looked at how are they traveling, and how far are they traveling. So this is if we had to do a segmentation based on this, there are 3, 4, 5 variables, right? If you have to create groups with this, you'll probably need 50 to 100 models. You don't need that. We're able to do it more efficiently, and more importantly, these segments optimize our prediction. Our objective here is this segmentation process is specific to improving our mode choice. How well can we predict the choice of each person in our data set? That is what governs the segmentation. The segmentation I showed there has nothing to do with the dependent variable. It doesn't care what you are modeling. Yeah, men and women are different, so we split the data. Or high income and low income. That does not necessarily select variables which improve our mode choice model. Here, we carefully are letting the data tell us which variables are important to better predict our model and estimating them. Okay? So, again, there are some software which run this model. I think Apollo has them team to do later class models also. But they are known to be a little quirky in the sense that you have to know how to estimate the model. So when you do the estimation process, you have to be careful. There are a lot of papers using latent class models in literature. So it is possible to develop them, and I think there's significant value in clearly being able to see how we are segmenting the population, and then using that to better understand the choices that we want. So we've used these models in safety, for example. When we are modeling injury severity, there are two types of crashes that happen with very low risk to the person. So they're mostly 90% chance is no injury that happens. Car gets damaged, but no injury. But then there are some high risk crashes where significant percentage of them go to the hospital, severe injuries and fatalities. So when you are able, if you are able to separate those out, so we'll see that the segment where people are under the influence of alcohol, not wearing the seat belt, going over speed limit. These are the folks that will go through the risky segment. And then there are others who are driving regularly, but again they get involved in crashes. So you are able to find two segments: the safe segment versus the risky segment within the process. So again, it's useful when you can do something like that, and also in other contexts, also it is useful. Same thing in another context in safety, you can look at roadway segments also. Like there are some roadway segments where crashes happen a lot. There are others. If you look at any data set for segment level crashes, there will be like 5% of roads which have a lot of crashes. Then the rest of them are either 0 or 1 or 2. So again, you can capture that relationship through a latent class model where you have a segment. There are characteristics of the segment that identify why it is more risky, and there are other characteristics why the others are not as risky, and you can model. Okay. Any questions? Yeah. So estimating these models can get tricky sometimes, and what you give as starting value. Remember, in our code we are giving zeros to start with, but if you are running a model with a lot of variables, if you start with zeros, it will take longer time. So what you could do is, let's say, when you run your model for 6 variables, you know what the coefficients are because you have the results. So you can put those as the starting value. Instead of putting 0 for all coefficient, you can put the convergence results from the previous iteration as your starting values, and only for the ones that you newly added, put a 0. So let's say I estimated my model with travel time and travel cost. Okay, and a constant. So I have those coefficients now for my model. So I can, instead of leaving them as zeros for every coefficient, I can enter the final values I got at convergence as the starting values. And for every new variable, so let's say I have travel time, travel cost, now I am adding number of transfers. So for number of transfers, I start with 0. But because you have given starting values that are optimized already, the log likelihood function will be much better at the starting point. Okay, so it will quickly find the solution. So that is the idea of why we even ask for zeros. Because it is to help you. It is to help you when you're running larger models. So for example, in one of the papers that we have like 80 to 90 parameters. So if you start everything at 0, it will take forever to converge. So what we do is, when we are at 30 or 40, we'll put those 30, 40 starting values and then add 10 more values. So that it can find those 10. You're helping the algorithm find answers quickly. So once you find the 10, you have 50 answers, then you add the next 10. Then add the next 10. That way you are facilitating quick estimation. But if you put 80 variables and put all of them 0, it will take for an hour to find the solution, especially for complex models. Okay? So that process becomes even more important when you're doing latent class models. Sometimes you can use what is called an expectation maximization algorithm or the EM algorithm. Apollo has the EM algorithm coded in that to make this efficient. I have found mixed benefits with it. I usually ask my students to run the code without the EM algorithm, but again, it's up to you. If it helps, you can work on it. Any questions? I'll skip the joint choice models in the interest of time. So I have a case study for this. You can read it if you're interested. And for now, because I want to get to model response models. So far we talked about categorical variables that are general. Right? Any categorical variable you can use a multinomial logic model. So it can be mode choice, it can be the survey response of Likert scale variables. MNL models are flexible in that they work for any categorical variable. Ordered response models are a class of models that work only for ordered variables, okay, or ordinal variables. So if you have vehicle ownership, it goes from 0, 1, 2, and 3. For that, you can use an ordered response model. Or you can think about injury severity. If a crash happens, the injury of the person can change from no injury, severe injury, fatality. So that is an ordering. As you go from one alternative to the next, you're actually progressing in the same spectrum. Okay. Or if you have any survey questions where you ask how satisfied you are, not at all satisfied, or to very satisfied. There are, again, that is also a natural ordering going from very negative to very positive, or very positive to very negative. So there you can use order response models. So in an order response model, what it's a little different than how do we come with the same problem. So in an MNL system, you have three alternatives. It's like this. So you are getting the utility here. You have three utility structures. So you create these bars and say, okay, this is the largest, so this is what is chosen. So this is the approach we use. So we're using comparisons like this. In an order response structure, we do it differently. What we do is there is a line like this. Three alternatives. We assume that there are two thresholds, and we divide it horizontally. What we are saying is, because there is a natural order, all I need to do is find the cutoff or threshold where the alternative changes. So if you are below that threshold, you are in this alternative. If you are above this threshold, you go to this alternative. If you cross this threshold also, you go to this alternative. So it changes based on how we use. So here there is epsilon 1, epsilon 2, epsilon. There are three error terms in this system. Every alternative has its own error. But here there is only one error. The whole process is managed with one random variable, and we use that to partition the alternative space into as many pieces as needed. So because they come from different processes, they are not equal. But when you only have two alternatives, both approaches will give you the same answer. So an ordered logic model with two alternatives or a binary logic model will be the same, as long as the error term is the same. Okay. But once you go beyond two, there is no equality. There is no relationship between them, and they are not the same models. Okay. So any questions? So the way the ordered response model works. Yeah. Yes. Yes. It is possible depending on the structure. We'll get it. Okay. I'll explain that. We'll talk about that as we go. So this is how we'll write the order response structure. So let me do that. So there is we hypothesize here that there is a propensity for participating in the activity or choices that we are modeling. And what we are saying is, if you have this, depending on how it relates to the threshold. So y is the observed value, observed ordinal variable, and we'll have thresholds that go from psi 1 to psi infinity. Using that, we can come up with the probability. So if you have only two alternatives, let me explain this. So we will say if this is greater than 0, so your alternatives are 0 and 1. If this is greater than 0, y is equal to 1. Otherwise, y is equal to. So if the propensity alpha plus beta x plus epsilon crosses 0, then you are choosing the first alternative. Okay. Now, because epsilon is a random variable, so probability that alpha plus beta x plus epsilon is greater than 0 is same as probability that epsilon is greater than minus of alpha plus. Okay. So this is the cumulative form, but it's not in the exact form we want because it is epsilon greater than. So this you can write it as 1 minus probability that epsilon is less than. So this is how you get the probability. So this is the probability for the y equal to 1. For y equal to 0, probability will simply be 1 minus of this. It will be probability that epsilon less than minus. Right? So there are two alternatives. So you will get the probabilities like this. So another way of looking at the same thing could be you have cutoff at 0, probability 0 and 1 are. So if the propensity is this side, you are looking at this area. Okay. Otherwise, you are looking at this. So this area is simply cumulative up to 0. This area is 1 minus the same. That's how we compute the probability for auto response with two alternatives. Okay. Now, if you have more than two alternatives, what will happen is it will the equation will change a little bit. So it will still look similar, but here we have less than or equal to 0, then y is equal to 0. Okay. There are two conditions as we keep going forward, right? So there are more alternatives. So sorry, a minus 1. Okay. Here I don't have to put less than or equal to because the last one is effectively infinity. So I only just look for this. So if you look at the threshold like this, 0, psi 1, 1, psi k minus 1. So if you have k alternatives, so the last one is I don't need any upper limit because that's infinite. So basically, as long as I'm greater than psi k minus 1, this is how it. So the probability now will not just be one term. So in the beginning, it will be one term. When you come here, the epsilon has to be greater than something and less than something. So there will be two terms. So probability of this minus that. So there will be this will be the larger probability. You will subtract from the smaller probability, which is actually what you will see here. Okay, so that sequence continues in that fashion. So let me show you the actual problem. If you have something like this, this is how the probability will be. Okay, so you have CDF of minus alpha plus beta x. You'll see there is a nice continuation. So this probability moves here. This moves here. This will move there. So it will keep. So when you are computing, there is a nice sequence of because we have already computed that. Just use it to compute the problem. So if you have 5 alternatives, you'll only because I'm using 0 as a threshold. I don't even need 4. I only need 3. So 0 is first alternative because I am adding a constant. So if I remove this constant, this won't be 0 anymore. This will be psi. Okay. Think of it this way. In a multinomial logic model, if you have 5 alternatives, how many constants can be estimated? 4. Right? One of them has to be 0. You can get 4 differences. Similarly, here, if you have 5 alternatives, I can do 1 constant and 3 more thresholds. There are only 4 degrees of freedom. When you have 5 alternatives, I can fix 4 degrees of freedom. So it could be 1 constant and 3 thresholds, or 0 constants and 4 thresholds. It's up to you. Okay. So if I don't have alpha here, this won't be 0. This will become psi. You go to psi 1, psi 2, psi k. Okay. That's how it will go. So once you get the CDF, if you use epsilon as a normal distribution, you will get a probit, ordered probit model. If you use a logistic distribution, you will get the ordered logic model. So the logarithmic function is exactly the same as what we did for MNL, and you can use it just like that, the way we used it in multinomial logic model for maximization and distribution. Okay. Any questions? So now the way to interpret this model, it's actually easier to interpret because it's a very simple structure. So if x has the beta is positive, what happens is if x increases, the curve moves to the right. So the probability for the first alternative goes down, probability for the last alternative goes up because the curve is moving to the right. Similarly, if it is negative, it moves to the left. So if you think about a safety model or a number of cars model, so vehicle ownership, as income increases, the beta is positive. So as income increases, more probability for higher vehicle ownership levels. As income decreases, so when you are estimating these thresholds, one thing to note, and this is what you also talked about, is there is a relationship between thresholds. Psi 1 has to be less than psi 2, has to be less than psi 3, less than psi 2. Okay, depending on the share. If your share for some of the alternatives is small, right? Because at the end of the day, what we are doing is we are doing the probability distribution limits. So if the probability for the last alternative is small, your psi 3 will be very close to infinity. If your share for the last alternative is, let's say, only 1%, then you can see a huge jump in the psi 1 value. That's why usually it happens. Okay? If your share for last alternative is very high, psi 1 will be very small. Okay, or psi 4. So this could be usually the way I see it. This is like -2, 1, 4. Something like that. This is common. Okay, this is, but in some cases where there are skewed shares, you can have issues where your thresholds become very large. It can happen, but I would still look at the data carefully if that happens. You said 400, right? That is still very high. I mean, you have some variable in your propensity, the beta x, that is pushing you. So yeah, you can do that, but it's not common for that to happen. I mean 400 is a lot. The largest threshold I have seen in my data sets around 10 or 11, but yeah, 400 seems very high because probability beyond 400 is 0. Okay, if you look at CDF of 400 itself is 0. So what is there's no probability left for the alternate. Maybe very few records are there in that alternate. No, they cannot. They are equal, it means the other alternative does not exist. So it means your sample has no record. It can only happen when you have no records in that alternative. So if psi 2 and psi 3 are equal, what you are saying is, so here I have psi 2, let's say. You are saying this line and this line is the same. That theoretically means there is no probability for this alternative, right? Which is there is no observed record. Yeah, only then it can happen. or not equal to, sorry. They shouldn't be equal. They have to be strictly less than. So now in this approach, the only degrees of freedom are on how the curve moves. Yeah, that's all. That does not. But that can come like this. So again, that also means you have very high. So for thresholds, so don't worry about that because all it's saying is, so what does odds ratio say? It says how far from zero that variable is. So all it is saying is this is very far from zero, which makes sense. It is very far because if your threshold is large, because it is significantly different. Right? So if you look at odds ratios for this, it will be less than, much less than this. If you have a threshold around 1, it will probably be close to 1. This will keep increasing. As the thresholds keep going that way, odds ratios will increase. But again, it is not interpretable in any way. It doesn't mean anything. Also, significance of thresholds is not important. Don't care whether they're significant or not. Because our significance is measured relative to 0. What we are doing when we are saying a variable is significant in the standard way is we are saying the variable is different, not different from 0. If you are saying the variable is insignificant, you are saying the independent variable that you tested for beta is not different from 0. But I don't care whether it is different from 0 or not. That, but these stats in software are computed towards 0 for 0, so they print that up. But we need to recognize that significance of that parameter has no meaning. Yes, you should. We don't need to mention. You should show the value. Yeah, no need to mention. It's not applicable. Marginally significant. So again, the most accurate approach would be to a log likelihood ratio test with and without the variable, each variable at it. Instead of doing so, once you put 4 or 5 together, even if one variable is significant, it might make the model might make all 5 of them important. But if you do it one variable at a time, both the significance from your t-statistic and log likelihood ratio should be similar. Usually, log likelihood ratio test is more reliable, but still, I'm yes. So, if you have a system like this, so this is an example thresholds I'm showing here. So minus 1.5, 0.25, 0.5, and so on. Okay. Now, in the so if you want to think about the comparison with MNL, what you notice is if you have two alternatives, both of them will give you the same results. The probabilities, everything will be exactly same. But once you go beyond 2, things will not be the same. Because you only have one equation, right? I only have one equation in the order response model. It doesn't matter how many alternatives I have. Usually, the order response model will outperform, will be efficient that way. But because there's only one equation, the traditional order response model will always underperform MNL model. Because in MNL model, you have more degrees of freedom, so it performs better compared to traditional order. Okay. So again, I have to discuss about that statement and so on. But I will not go into that. I also have some of you might be using, so you might be using ordinal models or you might be using count models. I have some material on count models. Is anybody working on count data? Okay, if not, I'll skip this also. I want to go to So again, as we will talk next, I'm starting the advanced module here. So we will talk about some of these frameworks where you can address the limitations of the multinomial logic model. Like we talked about taking class models. There are discrete continuous and multiple discrete extreme value models for different contexts. So we will see how much we can cover. So we talked about the issue with IIA property where if you have multiple alternatives, all that matters is the relationship between a pair of alternatives. It doesn't matter what happens to the other alternative. So that comes because we assume that epsilon n is independent. But it is possible that in some cases that is not true. So here I'll give you some examples. Right? So if you use a multinomial logic model for these four alternatives, you have all four independent error terms. Okay, but you can think of a case like this. So you can say this is a private alternative, this is a shared alternative. So there is something common across these three alternatives. So we can call that air, bus and rail might form what is called a nest. Okay, so there is something specific. So there is an error here, there is error here, but between these three alternatives there is some common error. Okay, and some separate error. Okay, so they also have some separation. It's not like bus is exactly same as rail. In that case, all three of them will be the same alternative. But in a nested logic model, what we are saying is we partition the error into two parts. We are saying these three shared alternatives have a common error and totally. So let's say this error is 100 units, just as an example. Each of them also should have error should be 100, but there is something like 30 common, 70 is independent. So that's the idea we are doing when you're talking about n nest. So we are saying we are trying to find what is the percentage that is common, what is the percentage that is not common. So if it is 100% common, then we will have to say, oh, these three are the same alternatives. If it is 0% common, we go back to this. We don't need that structure. Okay, so that is what we are trying to figure out when we do a nested logic model. Now, somebody might come and say, bus and rail might have even more common because again they are slow moving shared modes. Okay, so that's also possible. You can have a scenario like this. So what that does is, this is always, let's say it is 100, it stays at 100. There is 30 common here, so this is 70. There is another 20 common here, so this is 50 and 50, something like that. So that is the way you partition the correlation. Somebody might say there is air might be correlated both with car and others because it could be more control, if you can think of it that way, or price wise it's expensive versus this. There are some factors that it might be correlated with car, for some factors it might be correlated with bus or rail. Okay, but this we cannot handle with a nested logic model. For that you need something called a cross nested logic model or more advanced models. Okay, the first three can be accommodated within a nested logic model. The nested logic model, you can have any levels of hierarchy. Okay, depending on if you have 8 alternatives, you can probably have 3 nests. Okay, so that is possible. But one thing to note when you have a 2-level nest like this is the correlation that you have here should be less than the correlation here. Okay, if this is like, for example, I said, right, 100, 30 is common. So what is left is 70. So this 20 should be able to accommodate, should be less than that part. Okay, so there is a requirement that we call it the log sum parameter. The log sum parameter has to be smaller. Okay, because if this is larger, the model estimation might give you a larger value. Okay, I've seen published papers where they reported that this has a larger log sum than here. The reviewers did not see it, it got published, but that is wrong. You cannot have it. Objective function maximization wise, you might get a numerical value like that, but physically that is meaningless. So you have to be careful when you're doing nested logic models, because when you end up with a model, you need to make sure that physically it makes sense. So for that to happen, the hierarchy of the row parameters has to be maintained. So if this is 0.8, this has to be less than 0.8. Okay, if this comes out, when you optimize, sometimes you get 1.5. Again, all of them have to be less than 1, and the hierarchy has to be maintained, just like a threshold. Okay. So I'll explain how we do the formulation. Okay. So consider this 4 alternative case. Okay. So we have 4 alternatives: car, air, bus, and rail. So we start off with this. So U car is V car plus epsilon car. This is the independent one. We won't have to worry about this one. Now I write the other 3 with 2 parts. There is a common carrier part and the separate part. Again, the total variance of this should be equal to the variance of these 2 terms. It cannot change. That we cannot randomly keep adding things to our utilities, right? So whatever variance is there for the whole thing, these 2 will have that now. So they have to share that. That's why if that variance goes, if epsilon cc has a larger variance than epsilon car, that's physically not possible. That is what it's being said when you have your theta value greater than 1. When your theta is more than 1, you're saying, oh, I'm artificially increasing the error to create correlation. That is not physically possible. Mathematically, it can happen when you do the numerical analysis, but you have to understand that and not report that as a useful result. So overall error is still identical, right? So epsilon air is equal to epsilon a plus cc, all of that. So we maintain that. So what we are trying to do is find what is the common error. Now, if that common error is 0, then it's like without a nest. It's just all 4 of them are at the same level. So the bigger errors, the larger errors, we assume them to be Gumbel 0, 1. Okay. The smaller errors now, I assume to be Gumbel 0 theta. So for that variance, we have 1 as our variance. So anything I do with theta has to be less than 1. Okay. So that is what we are trying to show you. So it can go up to 1. If this theta goes to 1, what that tells you is all the error between these 3 alternatives is common. There is no independent part at all. Okay, but it cannot go more than 1. So at the same time, it can be 0. It cannot be less than 0. Okay. So I think that. Okay. Let me show. Okay. So we need to figure out what is the correlation between the error terms. So what I'm doing is, because this is 0, 1 and this is 0, theta, the common part has to be 1 square minus theta square. So it will come like that. So pi square of 6 minus pi square theta square by 6. So this would be the error variance for the common, the remaining independent part. Okay, this would be the independent part. So then your correlation is defined as covariance over this. So if you look at that, it'll end up being, correlation will be 1 minus theta square. Okay, so if theta is 0, there is perfect correlation. If theta is 1, there is no correlation. So this will be the correlation term. So whenever we are testing our hypothesis, our t statistic is not, for theta is not relative to 0, but it has to be relative to 1. You have to compute this separately. So in the software, it usually prints the t statistic relative to 0. What it does is it does beta minus 0 by standard error. But when you estimate this, you have to do beta minus 1 divided by standard error. Again, some software do it correctly, but you need to check, because our null hypothesis is there is no nesting, right? Because you have to prove beyond doubt that A, B, and C are correlated separately. So that's why our null hypothesis theta equal to 1. So you have to compute your t statistic relative to 1, not 0. Everybody okay with that? Okay, so now the way the probability works is you do it in parts. Okay, so let me show it here. So this is 1 and this is theta. Okay, so the probability, it's still multinomial logit. Okay, it's still the multinomial logit probability. So instead of saying this is e power v air, we will say it is e power v by theta, because it is, when theta was 1, we said it is e power v car. Okay, so when we initially did the probability, So when you have 4 alternatives, our probability was this. But this is because theta was equal to 1. So we did not have to write divided by 1, divided by 1. But now theta is actually theta. So our probability will be e power v1 by theta, v1 by theta plus v2 by theta plus v3 by theta. That's what I'm doing when I'm looking at the nest. So when we go to the nest for the 3 of them, it will be e power v1 by theta, v2 by theta, v3 by theta. That is easy. The challenge is I don't know which of those 3 are chosen. I have to, so the choice now is between car versus all 3. Okay, so to figure that out, I need to figure out maximum of the utilities of these 3 numbers, right? Because the competitor for car is the one which has the highest utility in these 3, right? So the user has to choose one out of these 3 that will compete with the car. I don't have to worry about ones that are lower. So I have to find the maximum of utility for the 3 of them. So that is usually a painful thing because you are doing max of 3 random variables. But for Gumbel, the max works out to a nice formula. So, I mean, that's why we are using nested logic, okay? Because I'll show you the formula. This is how the maximum works out. Okay, again, it's a 3 or 4 page proof. I'm not going into the details. So it will look like the max of v1 and v2 will be theta times ln of the summation of all of them. Okay, it is distributed like that. So now this is the first probability for the lowest nest. I need 2 parts, right? Because I need to determine between car and shade. How do I get to air, right? I get to air only if I get to the common carrier, right? So let me show you. To get the probability to here is 2 steps. One, I choose between car and shade, right? Then I come here. So when I came, I gave you the probability for this one, but I need to figure out what the probability is here. Okay, that is the next step. For that, I need utility of car and utility of the maximum of all these 3 of them. Then it's a binary choice. If I know the maximum of these, it's just a binary choice, right? Between car and then it becomes easy. So you'll get each probability will have 2 steps. So air probability will be air within this nest and probability of coming to this nest. Okay, car won't be like that. Car will be car plus whatever combo utility you get up there. It will be between those 2. That's all. It's a binary model. So car will be easy. The other 3 will be a little complicated. I'll show you. This is the utility. I'm just deriving the value. So it look like this. So car will be exponential of car plus some theta times some gamma log sum. Okay, I'll show you what that log sum is. So for shared one, it will be between VC and this because it's a binary model, right? So now what does that delta look like? That lamp gamma look like? I think I defined it in the previous. This is the gamma. So I'm not writing there, so it's easier to see. So it's simply ln of exponentials of the utility. Okay, so this is what goes into that term. So now with that, knowing that, you'll have everything you need. So if you know this one, okay, so you can compute that. Now if you want to see, if you set the theta is equal to 1, when you multiply this with this, it will actually collapse to e power v air by all the 4 exponentials. You can try that. It will simply collapse to what we get for a 4 alternative case. But whenever theta is different from 1, it will look something like this. It will be this multiplied with this. That is the property. Okay. So yeah. So I'm doing that when I put theta equal to 1. You'll see that exponential and ln will cancel off. So that 3 terms will cancel off with this 3 terms. And because again this and this ln and exponential, so this and this 2 will cancel off. this exponential and ln will cancel. So you will get the usual 1. So you will have exactly the simple MNLT that comes. Okay, if theta is equal to 1. So again, it shows you that nested logit model, if you restrict theta to be 1, it will be multinomial logit model. Okay, any questions? Yeah, so now I think I should have a slide. So if you do the IAA relationship here, if I do PI by PJ, okay, if you are for MNL, it will cancel off, right? The denominator cancels off. But here, it will not cancel off, because if you do the ratio between car and air, the air probability has a weird formula, right? So if you do air CC and rail CC, within the nest, it will cancel off. Yes. So between car and others, IAA is no longer a problem. But once you, within the same nest, we still have IAA, because the probability is still e power VA by the summation of all three, right? That denominator will cancel off. So that's what I'm saying here. It simplifies for the shared alternatives, the three alternatives in the nest, it will simplify like the MNL. But when you do it with car and air, it does not simplify. So between the nests, if I am changing the car share, all three of them are involved. Okay, but if I change car, the rail one, it might not be. When you do with rail and bus or rail and air, it's still IA. Okay, but with the outside one, it is no longer IA. So it reduces the IA property. Alternatives within this nest still act as if they are part of the MNL structure. They will act like that. But alternatives outside, they will have different substitution pattern. But even that is very helpful, because it will avoid the scenario that we talked about with the red bus and blue bus. So I'm showing again, elasticities for nested logit can get very complicated because the probability expression itself is messy. This is the probability expression, right? So we're taking derivatives for this one. So it can get complicated. Yeah, but there are software that do it for you. You don't have to do it. So I have some formulas here if you're interested. And again, the formula we derived is for one kind of nest, right? So if you want the other kind, so where these two go down, okay, the probability formula will become longer, right? Because there are three steps to get to rail. I have to get to common carrier, then to public transit, then to rail. So there is conditional on where you are. So there is a log sum going up once, there is a log sum going up twice, and then you get to the top. Okay, so the probability expression, my first effort to learn PhD was one of these models. So I remember spending multiple days writing the formulas for all of these things. So something like this. So I'm showing here. This is the mathematical process, right? So you have dA, that is only one. Then there is two parts for the second one. Then there are three parts for the third one. So it can get complicated that way. Yeah. So you have theta, then I put eta there. So eta has to be smaller than theta, theta has to be smaller than 1. Okay, that hierarchy has to be maintained. If that is violated, you don't have a feasible nesting structure. Okay, it doesn't matter if it's significant, it doesn't matter anything. If that order is not maintained, it's garbage. What you got for output is garbage. Okay. Yeah. So if you want probabilities for a structure like this, that chapter has the formulas. You can look it up. Again, nobody will memorize these things. You just write down if you have a case where you're working on something like that. Okay. But before you start estimating an nested logit model, okay, just because it's an advanced model, don't start with that. Do a good job with your multinomial logit model, then try nesting structures. Okay, sometimes nesting structures, thetas don't come significant. Like if you have a well-specified model, I think in my career in running nested logit models and other models, I think I got it significant only once ever. Okay, so because if you do a good multinomial logit model, you don't need a nested logit model. It does not come significant. If you are trying all the independent variables you have in your data set carefully, in the Indian context, because there are a lot of missing variables, you might end up getting it. But I think if you do a good job with MNL, it helps. Then attempt to incorporate. So start with systematic effects. Systematic effects are observed variables, your X's. So lay more emphasis on your beta X and X's. So do a good job with that. Then try for the theta, eta if you want. Okay. So if you, that's when it helps. Sometimes you'll end up with a theta greater than 1. That means the formulation is not consistent with utility framework. Okay. So, yeah. So, okay. So there is more material on GEV class of models. So these are advanced models that make nested logit as one of the simplest versions. There are more advanced versions of that. So in the next segment, so in the afternoon seminar tutorial today in the lab, we'll work on codes for multinomial logit and ordered logit. Tomorrow I'll quickly give a glimpse of this, and we'll talk about machine learning models also. And I don't think we'll have time to do tutorials for machine learning models, but I have codes that I've prepared that I'll share with you that you can use when you have time. Okay, folks. So we'll break for lunch. Thank you.